Good morning or good afternoon, everyone. I'm Megan Matheson. I'm the co-lead of the Canadian Marine Shipping Risk Forum Community of Practice and also the Director of Strategy and Engagement for Clear Seas. I'd like to note that the session will be recorded and the recording will be posted on our website along with the presentation slides after this meeting. And everyone who registered will be notified once the recording is available. Before we officially get started today, I'd like to take a moment to acknowledge that I'm joining this session from the traditional ancestral lands of the Snuneymuxw and the Snuneymuxw First Nations on Vancouver Island, and I'd like to express my gratitude for their stewardship of these lands and waters since time immemorial. To introduce the Canadian Marine Shipping Risk Forum, it's a community of practice that was launched in 2019 with the support of MEOPAR, the Marine Environmental Observation, Prediction and Response Network, and hosted by Clear Seas. The community of practice is open to all who are interested in the work of understanding and mitigating shipping risk. Thank you for joining today's webinar. It is a part of a series that is focused on technology and its role in mitigating shipping risks. If you missed any of the previous sessions, which there are now many of, you can go and find them on our website, and I'll put the link in the chat. And also, if you'd like to be notified for any future webinars on these sorts of topics, you can sign up for the mailing list, and the link is also in the chat there. I'd like to ask everyone to remain muted for the presentation, and then afterwards we'll have some time for Q&A, so please feel free to come on video if you'd like, unmute, raise your hand, ask questions, or if you'd prefer, you can type your questions into the chat function, and I'd be happy to read it out on your behalf. All right, on to our presentation. I'm very pleased to welcome Meg Batchelor, who is the lead for the Halifax branch of OMC International, and she has over 18 years of expertise in maritime and systems engineering. Specializing in port operations and complex data modeling, she's worked on UKC systems under Keel clearance, channel design, and system diagnostics. Meg has contributed to a variety of projects, including channel risk optimization and AI-based mid-ocean forecasting. And I'm very pleased to hand over to her to take us through integrated maritime risk management.
Well, thank you, Megan. Hi everyone, I'm Meg. I'm a project engineer at OMC International, and I'm based in Halifax. Today I'm going to talk about a few cases involving ship risk mitigation from the keel to the mast. Before I get into the details, I do want to give you a bit of a background about who we are and the kind of work that we do, because it sets the scene for the examples that I'm going to be sharing today. OMC has been around since 93. We started in Australia, but we have teams in Halifax and Europe as well now. Our work sits at the intersection of maritime operations, data and safety. And a lot of what we do is research driven, but it's grounded in real operational needs. So our systems are for the day-to-day decisions that pilots, VTS operators and port planners have to make. Our best known product is DUKC, so that's what we're known for, our dynamic underkeel clearance system, which has been around since 1993. But we also support ports with a range of operational safety tools, engineering studies, and also one-off problem-solving projects. Recently, we've been involved in the international standard work as well, including representation for the IHO S100 project for the S129 underkeel clearance layer. So today we'll walk through three real-world examples of our technology. So managing underkeel clearance and bridge clearance in Savannah, addressing dynamic mooring at swell-exposed berths, and our latest air draft warning system in Melbourne. So the first one, Savannah. It's a narrow river, a big bridge, and ever bigger ships. This is a map of the channel. The black is the shipping channel. The ships come in down on the east. They go through a 600-meter channel that slowly gets narrower to around just over 200 meters near downtown. Then they have to pass a bridge just past downtown to get to their main terminal where they get the containers on and off the ships. So this presents a problem for the pilots. So they have to manage multiple risks at the same time. They have operational constraints, both in the horizontal and the vertical. So while the maintained depth is 43 feet. Constant sedimentation creates a persistent underkill clearance risk between dredging cycles, with little shoals coming into the channel or bigger ones. Additionally, there is a risk of bridge strike due to vessel air draft, and strong currents in the narrow channel create a risk of losing steerage. So the pilots have to determine the safe sailing windows while maintaining industry pressure for the deeper drafts. So the real question becomes, when is it actually safe to move the vessel? Is it safe when it's tide's highest, or is it safe when the tide's in the middle of the stage? There's many factors, and all of the factors together, underkill clearance, steerage, bridge, water currents, they all come together to create a bigger picture. So to solve the problem of when they can actually safely sail, we started by taking vessel motion measurements to determine the real underkill clearance between the seabed and the vessel keel. So a few years ago, I was on this ship here and we were taking measurements. This is a GPS unit. We have a few of those on the ship and we're coming into the berth. So it's at the end of a measurement campaign. You can see the channel. It's fairly narrow and very muddy as well because of the constant sedimentation. So we extracted the information from those measurements to determine the vessel keel for each transit relative to the depth. So this higher depth is the minimum depth in each part of the channel, and this lower line is the depth under the keel. So they actually had more water. This is the underkill clearance between the keel and the depth. So this data from these the vessel measurements informed a custom DKC system. So for that, we developed models for underkill clearance and safe steerage that are specific to each vessel that transits the Savannah Channel and specific to each part of the channel. We built a custom DKC that incorporated the real-time and forecast water density, the water currents, the tides, the air gap at the bridge, the vessel speeds, and the ever-changing bathymetry. So combining the weather, so weather, tide, and everything, and the vessel models, and the latest bathymetry and air gap clearance, this gives optimized operational windows and reduce the risk of incidents due to the reduction in unknowns and the increased situational awareness that it results. The resulting tool provides vessel and weather-specific safe operational windows. They're not tidal windows, they're operational, and it might be at any stage of the tide depending on where we are. So this is a safe operational window. They can commence their transit from pilot boarding ground anytime from here to here, or from here to here, which allows them to avoid the risk of hitting the bridge or encountering strong currents while maintaining underkill clearance. The tool also allows the pilots to visualize trouble spots for targeted dredging, to open operational windows, and also while highlighting areas of greater UKC risk as they're planning their transit. So this is an example of a high spot in the channel along their path, and it's close to their keel. Finally, for Savannah, we implemented real-time monitoring to alert the pilots if the conditions become unsafe while they're underway. Here's some examples of DKC highlighting transits that are breaching or safe. These are all simulations, they're not real scenarios. The pilots are safe. But here is in our system, it's showing that there might be some red in this location. Red means that the underkill clearance in this location is iffy, probably might not want to sail there. And same for here, based on the weather conditions and the time of the tide. And this is another representation of that. Here is a representation showing the green shows all this channel is safe based on the operational defined channel, but they shouldn't deviate from the channel because if they do, these red areas are areas of no-go. Here is an example of the no-go areas loaded in the pilot's PPU. They use CIQ, which is we've been trialing with showing S129 underkill clearance layers. So the S129 layer is loaded into the PPU and it updates based on the vessel's estimated time at each location and the weather conditions in real time. So pilot comes here and it says here is the area to avoid and then it moves over here, and maybe it speeds up, or maybe the tide's full, and it says, okay, this area is now to be avoided. So that's coming soon. S129 will be available in CRQ in about, I think, a month, maybe two, and it will be rolled out for Savannah. So the outcome for Savannah is a greater situational awareness and a reduced risk of grounding, steerage loss, or bridge strikes. The system does allow the port to identify specific shoals for targeted dredging and provides the flexibility to widen operational windows or increase vessel drafts when the conditions permit. So that was a case study in vessels transiting with underkill clearance concerns and bridge concerns. The next study is about concerns with berth. So this is a client that is a bulk export port with berths that are exposed to the open ocean conditions. They have significant vessel motions on occasion, and they needed a clearer way to understand berthside risk, distinguishing situations where it was genuinely unsafe to remain alongside from those where conditions appeared uncomfortable or were still within safe limits. And they were wondering about, is it okay now? Should we be deberthing now? Is there bad weather coming in 24 hours? So they're not sure exactly what the situation was. So what we did for them is we did a dynamic mooring analysis to create custom models for the specific vessels, load states, and the lines on the berth, so the way that the vessel is tied up at the berth. With that, we identified infragravity long waves as the primary risk factor and installed specialized sensors to detect and forecast these waves. So they're a bit sneaky. They're kind of hard to see from the berth, and they're not that simple to detect from typical wave sensors. They sort of lie somewhere between a tide and a wave. So it's sort of not usually something that people consider too much. But for swell exposed ports, it can be quite a significant factor. So taking into account this infragravity waves and also the wind and the normal waves, so swell and sea waves for these particular berths, we came up with a live berth warning system that incorporates the mooring models and the real-time and forecast weather conditions for those berths. Here is an example of a mooring live berth warning system in effect. So this is they've chosen the scenario A. So this is the line load state and the vessel that they've got. And this is showing you the warnings. This is an example where right now it is in a warning state. They have to be pretty cautious. It's going into the red. So this is the percent risk of vessel motions at the berth that might cause damage. And then it's forecast that around here, it might be a little bit bad again. And then over the long term, they should be able to be bringing the ship back to berth. Here's an example of some of the weather. So this is the long waves, infragravity, and this is the swell height. In this case, the infragravity is 10 centimeters while the swell is 60 centimeters. So the conditions aren't too bad for that particular example, but that's not associated with that. There's two different examples, but this infragravity wave height can be quite high. So the outcome of implementing this live berth warning system is it results in greater situational awareness for the operators on the berth and can reduce the risk of injury from lines breaking or infrastructure damage while minimizing the unnecessary operational interruptions of deberthing. I know I'm going through this fairly fast, but I did want to squeeze a lot of information into 20 minutes. So this is the last case study I'm going to talk about today. This is Melbourne in Australia. This is where I come from. Their concern there was the overhead clearance at the Westgate Bridge. So I was talking about Savannah and how they're concerned about hitting the bridge, but they get an air draft and they have air draft sensors, and then we would calculate the air gap. So at Melbourne, they already have the air gap sensors on the bridge. They have the calculated air gap, but the challenge was actually on the vessel side. The air draft, the reported air draft, isn't always reported accurately, especially when the antennas or equipment change. Well, the air gap and the tide height is known, and in the case of Melbourne, the underkill clearance, the air draft reported by the ship is the unknown. And then we did see visual evidence of vessels scraping the underside of the bridge, so there was a real concern. So the solution was a collaboration between OMC and Ports Victoria. And we used a hardware setup based on LiDAR scanners. So these are the LiDAR scanners. So we had a few scanners. They create a point cloud image of the vessel as it approaches. What you're seeing here is an example of that point cloud. It's elongated because of the way it scans it as the vessel goes past. From this data, we can accurately determine the vessel's air draft in real time. So here is a LiDAR scanner at Breakwater Pier. That's down at the bottom of the port river entrance, and it's detecting the ship as it goes past and it's scanning. And it's detected by AIS triggers and then does a 2D scan and then a 3D scan. So the system measures the air draft about 23 minutes before the estimated time of arrival at the bridge. This gives sufficient time to alert the pilot and to divert to a safe berth. So in this case, here is the LiDAR sensor, and the ship comes past here, and it scans it, and then it will send off a message to the alert system saying whether the air draft is less than 50.1 meters, whether it's close to 50.1 meters, or whether it's over 50.1 meters. So if it detects that the air draft is over 50.1 meters, that's not clear. It'll send an alert to the vessel traffic service and the pilots, and then they will take an abort action that is already in the procedures. So they would abort to the web dock, which does not go under the bridge. So the outcome from this is that several vessels were actually detected exceeding the port's 50.1 meter air draft limit. And this led to a number of aborted transits. We also saw that the measured air draft was several meters higher than what had been officially reported for a number of the vessels. Though those weren't necessarily in breach of the 50.1 meter requirement, they were significantly different from what was reported to Ports Victoria. In most of the cases where there were large differences between the measured air draft and the reported air draft, the issue came down to the measurement from, or the report from the ship missing an antenna when they were sending the value to to Ports Victoria. So this was resulting in underreported vessel heights. So this is an example of some of the antennas you can get up here, and even something like this has to be considered part of the measured air draft. Because our system can measure antennas, this is why we did detect that there was some vessels where the air draft that was measured exceeded that of the reported values to Ports Victoria. I am already finished. So across these three studies, we were looking at vessel risk in both the horizontal and the vertical plane. Each example shows that the different ports face different operational challenges. And I showed how some of the real-time measurements can help identify where these risks actually lie, whether it's in the under-keel clearance, vessel motions at berth, bridge clearance, steerage, or air draft differences between measured and reported values. So the purpose is the same for all of these case studies, to help provide accurate information to the operators so that they can make safer and more informed decisions. Thanks for your time today. I'm going to hand back over to Megan.
Thanks so much, Meg. That was really interesting. I appreciate getting to see all those different examples around the world of where this technology has been put into place to prevent incidents and strikes and other mishaps from happening. I'll just let everybody know again, if you join during the presentation, feel free to raise your hand, come on video, unmute if you'd like to ask any questions that you'd like to ask about this technology or the work that OMC International is doing to reduce risk. Or feel free to type your message in the chat and I'd be happy to read it out on your behalf. While people take a moment to think about any questions they'd like to ask, when you were talking about the Savannah case study, you said you were like on the ship taking measurements. How long does that take to gather enough data to then be able to create the kinds of models and systems? Like, what kind of time frame did the bridge clearance project take in Savannah?
Yep. So the measurements for that weren't for the bridge clearance, more for the underkill clearance, because the bridge clearance had more fixed operational limits in this particular case. So we were measuring primarily to check that the keel was safe. Um, for that, we did 6 vessels for Savannah. We did a number of vessels, and part of it is validation because we already have models collected from doing years and years of these measurements, combined with uh, vessel physics and dynamic motions and all the hydro. There's a word which I've forgotten right now, but yes, hydrological information, the way that the vessels squat in the river, all that data has already been collected and modelled. So what we were doing when we do these 6 measurements is validating and comparing Savannah to those existing models and tuning them because we know that different channels have different profiles for sinkage due to the Bernoulli effect of water coming around it and pulling the ship down, for example.
Mm-hmm.
Yeah, so for Savannah, it only took 2 or 3 weeks to do that. But depending on the complexity of the port and the variety of ships, we might do a lot more measurements.
So the six ships that you measured, would those be considered representative of the types of ships calling on the Savannah
Yeah.
port?
Yep. So they were targeted as the types of ships that are of most concern for them.
Right, the ones most likely to be in exceedance of the available
Of the different
clearance.
limits. Yes.
All right, we have a question from Robert Booth. What is the maximum reliable range distance that you've experienced with the shore-based LiDAR sensors to accurately report a vessel? How
Yes.
far can you
So
get?
my colleague in Melbourne did this project, so he's unfortunately asleep right now, so I can't ask him. Um, but it is, I believe, 2 kilometers was a working distance.
Okay, cool.
But because of the profile of Melbourne, you couldn't mount the LiDAR on a bridge or anything and look out 2 kilometers. So there's curves in the channel and it wouldn't be able to detect the ship.
So that's why you put it a little sooner in the path to be able to,
That and yes, yes, and it gives us more warning before
yeah.
it's too
Yes,
late to
it's
abort.
hard to stop a ship really
Yeah.
quickly.
So if we had it on the bridge, there was multiple reasons that that wasn't the best solution.
Yeah.
Yeah.
Was it another like port fixture that you were able to put it on, or did you have to come up with a mounting
There was
tower?
existing port infrastructure that we could put all the lidars on.
Oh, that's handy.
Yeah.
A question from Jack Gallagher. Jack, go ahead.
Yes, hello. Thank you so much. Now I have to go look up intergravity long waves. It's a new term. So thank you for that. But my question was, when you're looking at the underkeel clearance information, are you using the charted information? Are you using your own multi-beam data or field sheets? And are you verifying that with the ships, what the ship's reading, or what are you using for that underkeel clearance?
Um, so for measuring or for modeling?
Both.
Okay, so for measuring, we are using the latest bathymetry data that we have and assuming that that bathymetry data is correct. It's not the chart, it's more like an S102. So it's a full bathymetric surface. And we're collecting all the tide information along the way. And they are lucky to have tide gauges all along the way. So you know where the tide plane is. And then from there, it's easy to extract where the, well, not that easy, but you can extract where the lowest keel elevation is. But that does assume that the draft that we've been provided is correct.
Yeah. Okay. So are you verifying that in real time with the ship sounder? Is that feeding
No,
into?
we found because our models are designed to be conservative, we know that the underkill clearance is actually going to be deeper. So the ship sounders just verify that information.
So you're using more like a chart datum, which always has that safety margin built in.
We don't really have access to the live chart, the chart, the thing on the, sorry, the sonar on the ships. So, but we have observed that the data usually, it says that there's more clearance. And so the
Okay.
ships might say, hey, it says there's lots more. And we're like, yes, we know, but this is the clearance relative to a conservative model and including allowances for uncertainty.
Okay. All right. And just another site, did you have any issues with integrating the information into the pilot CQ? Because we've had really good results with that.
So with like CIQ,
Yeah.
so our work with CIQ is fairly recent. We haven't had any overlap in clients until I guess the last few years. So we found integration pretty easy. There's a fast turnaround in displaying the correct information and been fairly easy to work with. But we've also worked with other providers as well who've adopted various information layers from us in the past.
Okay. Uh, One last question. When you're doing the horizontal measurement of the ship, what information are you using for that? Because I know when pilots go aboard, they have to put in offsets because of where the antenna are and where the turning point of the ship is. So are you using what the pilots use, or are you using something else?
For the horizontal, as in working out whether the side of the ship is safe.
Yeah, where the ship is in the channel. Yeah.
So the way we do measurements, we are measuring the horizontal and the vertical motions of the ship while underway, and we measure the where we place our equipment relative to the ship, and therefore we know where the ship is in the channel because we have three GPS signals coming in to align with. So we're not using the
Okay.
AIS for that position.
Okay. Very good. Thank you.
To pick up on the question of kind of how that information gets integrated into how the pilots can use this information, because thinking about well, I guess all the cases really, but the one where, is it going to hit the bridge in Melbourne? You need to know that information in advance so you can pull off to a safe berth or alter the ship's course in some way so you don't go into the bridge. How is that information getting to the pilots, and were there any challenges or issues with getting pilots to feel comfortable with this information, to trust it? Like what kind of, I guess, ground truthing or verification is done so that people can feel really confident in relying on this information that's getting provided to them?
Yeah, so that's a good question. I don't fully know the answer to. Um, I don't know what the pilot's response was to being told that they have to abort the transits. So I haven't actually talked to them since this was rolled out. I've been up in Canada instead, so talking to different pilots. But the process in Melbourne is that the vessel traffic service acts like an air traffic controller, and the pilots are like the airplane pilots. So well, the pilots are in charge of the ship. They also take instruction from the vessel traffic service to be alerted of any hazards that they might need to respond to, whether that's the bridge or anything else that might come along. And there is I guess, a trust relationship between the two, so that they know that the vessel traffic service has done their checks and made sure that that data looks somewhat right before alerting to the pilot that they might need to consider aborting the transit.
On another topic, thinking about you mentioned that with the Savannah case study, looking at the under basically the bathymetry and the shoals, ports could use that information to identify if there's spots that need targeted dredging, if there's getting a lot of buildup or something. So is there constant monitoring in place to be able to identify that? Like when for that particular case, is there something scanning the seabed constantly to be able to help that?
We wish. So one of the challenges in America is the US Army Corps of Engineers that does the surveying and I believe the dredging.
Hmm.
And the
They do.
challenge is because it is government, there is only so much funding. It means all the ports have to fight to get the resources.
Mm.
So, well, I think the port would love to have surveying on a daily basis. It's more like every 2 to 3 weeks, depending on the spots that were last known to
Oh,
be
okay.
shown.
That's
And
still
as soon as that data
fairly.
is released, we get access to it.
Yeah. Yeah, for
Yeah.
sure. Cool. Um, Thinking a little bit closer to home, before this webinar, we talked about some of the work that you're doing in Halifax to help ships enter more safely. Is there anything that you can talk about how some of this technology is being applied in Canada right now?
Yeah, so we do have a trial at Halifax. I can't talk too much about it because it's just a trial at the moment, but their challenges are somewhat similar and somewhat different to Savannah. They have waves, whereas Savannah is a sheltered port, And when you have waves, there's a lot more uncertainty in where your keel might be over shoals. So there's only one spot in Halifax where that might be a concern, and they have a way that they manage that by avoiding that completely. But they also have a bridge, and they tackle the problem differently to Melbourne or Savannah, and they have a live air gap sensor that we're currently in a project. We're trying to figure out how to make the forecasting of air gap better to help planning, but they have different rules based on the fog conditions, for example, and this isn't a problem for Melbourne. And they also have different, so they have different air gap, and so you just have to check that the ship's sufficient clearance to the air gap, whereas Melbourne's got a fixed limit. It says your air draft cannot be more than 50.1 meters.
Right.
Yeah. But
Thinking
it's,
about fog
that's it.
Think about fog. Are your sensors and scanners and technology able to work in those kinds of conditions? Are they able to still see the ship even in dense fog conditions?
I can say that Melbourne doesn't have quite as much fog as Halifax. Halifax is probably the foggiest place I've ever seen.
Yeah.
But it is designed to work in fog because Melbourne does also have problems with fog and visibility being a colder climate as well. But
And I guess given the kinds of distances you're dealing with, if it's under 2 kilometers, probably there's not much in the way of fog conditions that could be problematic at that range.
I'm not going to answer that one because I don't
Okay.
know for sure because I haven't tested Halifax fog.
Fair.
But the
That is the
Melbourne
fog.
fog I think it's okay with. Yeah.
You mentioned that the LiDAR that you're using has the level of sensitivity necessary to measure antennas, and those are pretty small. Is that like a higher grade, or is it more costly, or does it take more effort to scan at that level?
Yeah, so to scan for the resolution of antennas, I think we have gone for some very nice LiDAR scanners. They're not cheap to install or to purchase for that matter. Melbourne was quite happy to spend what it takes to get the real air draft values. But yeah, it's not a super affordable solution, but if the antenna is not so much concern, I'm sure that a smaller or a more affordable LiDAR would do the job.
Or I guess if you had more room to play with in it weren't as concerned about the antenna
Yeah,
scraping.
exactly.
Yeah, but when you're maxing out your allowable space, you've got to be really precise. Sounds
Yeah,
like.
exactly. Yeah, particularly for older bridges.
Yeah, they can be more delicate. Don't
Yeah.
want to mess with them. Any other questions from the audience? Feel free to share your thoughts. Anybody have experience using any technology like this from a pilotage perspective? Looks like you have answered all the possible questions.
Wonderful. Yeah.
Okay. Wondering, is there anything else that you maybe wanted to get to but didn't have a chance to that you want to add to this before we wrap up?
I'm going to be speaking at the Canadian Hydrographic in more detail about the S129 project.
Cool.
So that's the representation of underkill clearance in the visual space for ECDIS displays or PPUs. So I won't go into it too much today, but yeah, it's
When is that conference?
that's next week. So I'll be speaking next Tuesday. So if anyone's in Montreal next week, come and listen to me talk about S129 for 15 to 20 minutes as well.
Fantastic.
And also a really good lineup of other stuff to do with hydrography and
Yeah, if you're
bathymetry and
interested in bathymetry and data and
yeah,
ECDIS and
and
charts and things,
technology,
it's
come
the
along to Montreal. Yep,
place to be. All right.
exactly.
Um, Yeah, I think the maybe last question is you mentioned the infragravity long waves. I've never actually heard of that before. Is that a common thing? Is that more specific to this particular exposed kind of berth that would be, or is this a challenge that's fairly common to ports?
Um, for us, a lot of our ports are exposed to the elements, so they're sort of built out into the sea. Um, so infragravity does play a role for probably at least eight. I'm going to say with 8 ports, but it could be more or less. That's what I'm aware of now. And yeah, the infragravity and far infragravity, I'm not fully across what defines a far infragravity or an infragravity wave, but I know it's a really long wave period. So a typical wind wave is up to, 8 seconds or something like that. So you see a peak every 8 seconds. A swell wave is somewhere between 8 and 20, and that's the surfing waves. And then as you get into the longer wave, greater than 20 seconds, probably more greater than 50 seconds, but less than a tidal signal. Yeah, so that area is less well measured by typical sensors. We do work with special providers of sensors that are designed to pick up long waves for a number of our clients to fill that gap. But yeah, they're caused by storms or events way offshore that is slowly rolling through.
It just takes a longer time to get where they're going.
Yeah, and I've forgotten the specific details of that, but my MedOcean team will be happy to answer any questions on that if you ever want to reach out to them.
Fantastic. Robert's got another question about the Arctic environment. Have you done any testing or experience with the equipment that you're using in Arctic conditions?
No, we'd love to, but we haven't had the opportunity to. We haven't even experienced anything where we've had to worry about ice with our sensors. So I'm talking to ports in Canada now, and they're like, "Oh, we can't put in these sensors because the ice knocks them out." And this is something coming from Australia where you don't have to worry about this stuff. So we're still learning about that environment, and if there's a need to tackle that, we'll figure out a way. But we haven't encountered those conditions yet.
Well, there are lots of ports in Canada where that could be tested out,
Oh yeah,
at least on the east side.
yeah. Luckily, there's less shipping when everything's frozen over.
Yes, yeah, but I guess maybe on the shoulders as people are trying to stretch the shipping
Yep,
season a
yep.
little
And they
bit.
are stretching the shipping.
That could
Yeah,
be a really interesting test case to see, like, can ships get into Quebec or um, other potentially ice choked areas if they, yeah, if they
yeah.
had more accurate data to help support their decisions.
More data is always better,
Oh, absolutely. I'm on
even
that
if you
train
don't use
for
it.
that ship. It's a
Yeah,
ship, day ship.
yeah.
All right. Well, thank you so much, Meg. I really appreciate you taking the time to share those case studies, and it's really interesting to see it being applied in different scenarios, and then imagine, what other scenarios are out there that having this kind of data could really help decision makers and pilots and ship operators be able to be more informed and to have that peace of mind that no, you are not going to scrape this bridge as you go under it,
Yeah,
instead of just holding your breath and hoping.
that's the end goal. Yep.
Yeah, yeah, fantastic. All right. Well,
Cool.
thanks everyone for being here and participating today. We'll have the recording and slides up on the website soon, and we'll send out the link to everybody who registered. And we will be looking for more topics on navigational safety and technology coming up. So if anybody has any suggestions or knows of anything cool that we should talk about, please let me know. And if you want to be notified the next time we have one of these webinars, please sign up for the mailing list. The link is in the chat if you scroll up a bit, and then you'll get a notice when there's another webinar coming. Have a great day, everybody.